Okay, but this is the general strategy. So just to refresh ourselves on how this works, here's an example I want you to try out on your own. Find the point, x, y, z, that minimizes this function. Okay, and note that I'm asking for the minimizing output as well. Okay, so the x and y that minimize this function, and z, the value of that function at its minimum as well. Take a few minutes, discuss with the people near you, and we'll take it up. Okay. So it's actually possible to minimize this function without using calculus. We'll use calculus to do it, but you can do it without calculus. And I want to briefly talk about that way, just because it's a good life skill, but also because you're implicitly doing it in homework 1 already, in question 5. What's the strategy for minimizing this without calculus? Any ideas? It's called completing the square. What does that involve? Well, you can look at x squared minus 8x and say, well, that looks an awful lot like what I would get if I had x minus 4 squared. What's the issue? This is not exactly this, because this term down here gives me an extra plus 16 when I expand it out. So to account for that, I do minus 16. This looks a lot like what I would get. Well, maybe I'll say this. If I did y plus 3 squared. Because when I expand this out, I would get y squared plus 6y plus 9. There's an extra plus 9 there. So to compensate, I got to do minus 9. Right? And then I still have that minus 7 all the way back there. What does this let me do? It lets me write this as x minus 4 squared plus y plus 3 squared minus 16 minus 9 minus 7, it's minus 32. And that tells me without calculus that this function is minimized at the point 4, negative 3, negative 32. Why? Like, why does this imply this? Yes, and remind us of your name. Ju1. Close. It has to do with the fact that I've written my function as something that has to be greater than or equal to 0 plus something that has to be greater than or equal to 0 plus a constant. The constant can't be changed. And we know that the smallest value you could get of this first part is 0. Like it's not one of those functions that goes to infinity forever in the negative direction. something squared has to be greater than or equal to 0. So the way to make the output as small as possible is to make that term 0, which happens when x is 4, and that term 0, which happens when y is negative 3. So that's a way to minimize this function without calculus. Okay? Talking about that now? Well, it's because it's the kind of thing that appears in homework, right? Like this is essentially what you do in the last part of question 5 in homework 1. Okay? But that's not the focus here. We'll use calculus. Okay? Using calculus, you need to find the partial derivatives with respect to both variables. Now, sometimes you'll see it being written this way, but I'm going to write it this way because it'll be more consistent with what we're doing after. What's the partial derivative with respect to x? Well, what's the derivative of this whole thing with respect to x? To me, it looks like 2x minus 8. I also need the partial derivative with respect to y. To me, that looks like 2y plus 6. When I set 2x minus 8 to 0, I get x is 4. And when I set 2y plus 6 to 0, I get y is negative 3. And so my function is minimize at x equals 4, y equals negative 3. Okay? So this is the strategy we're going to use moving forward. Okay? Because this doesn't apply in all situations. Questions with the approach? Because all we're about to do is a more complicated version of this. I mean, it's much more complicated, but this is the general idea. Noah?
Is the optimizing on a boundary, is that only if it's defined over a domain? I forget.
I think you're thinking about the idea of a Lagrange multiplier.
Yeah, possibly.
Yeah, that involves optimizing when there's a constraint on what the x could be or y could be, but that's not the kind of issue we're dealing with here. Yeah. Okay, so here's what's going on. This is my function that has two unknowns, or two input variables, w0 and w1. And I want to find the inputs that minimize the output of this function. And to do that, I'm going to find two partial derivatives, one with respect to w0 and one with respect to w1. And I'm going to set both of those partial derivatives equal to 0 and solve the resulting system of equations to find the w0 and w1 that satisfy those two equations. And the results will be w0 star, the best intercept, and w1 star, the best slope. That's the plan. Okay? So let's get started on it. What I want you to do is that first step, taking the partial derivative of our mean squared error with respect to w0. When you do so, which of these four options do you get? Work on it with the people near you, and we'll take it up in a few minutes. Vote. Give us another 30 seconds or so. Okay. So all of the answers were either C or D. Okay? And indeed, one of those two is correct. But the reason you should narrow it down to one of those two is because of the negative 2 over n in front. Okay, that should look familiar. Where did we see it before? We saw it when minimizing mean squared error with the constant model, right? Because when you have something squared, the derivative becomes 2 times something, so that's where the 2 comes from. Okay? But let's figure out concretely what it is here. The derivative, or partial derivative, of this thing with respect to w naught is, well, I have something squared. The derivative of something squared is 2 times something times the derivative of something. So the 2 comes down. And then I need to multiply this by the derivative of this with respect to w naught. And what is the derivative of this with respect to w naught? It's negative 1, right? The coefficient on w naught, if you expand, is negative 1. And so I multiply this by negative 1. And so now I have several constants that I can pull out of the sum. That can come out here, and this can come out here. And so this ends up being negative 2 over n times this sum. Sound okay? That is the partial derivative of our mean squared error with respect to w naught. Okay? That's just half of the puzzle. We also need to find the partial derivative of mean squared error with respect to w1. And it's going to be slightly more complicated because here w naught wasn't being multiplied by anything. Well, I guess it was being multiplied by 1, whereas w1 is being multiplied by something. So that'll make it slightly more complicated, but largely the same process follows. Still 1 over n times the sum of 2 yi minus w naught plus w1 xi. Now, what's the coefficient on w1 if you expand? Good. So I can put a negative. Oops. Xi here. So now I have several constants that I can pull out. I can pull out this and this. So I can write this as negative 2xi over n or can I? What did I do incorrectly? Juan.
You put xi in the summation.
Why can't I do that?
Because it has the I in derivation.
Exactly. This xi has no meaning outside of our sum. Right? It's not a constant. Constants are things that don't involve i's here, right? And so that was invalid. The xi needs to stay out here. Okay? And one thing I'll point out here that someone asked about in the first section is the xi part of the summation? Indeed it is. If you like, you could think of this as having another entire set of parentheses. Okay? So the xi is very much part of the summation. So we'll say entire thing. Well, yeah, I'll leave it like that. But we found now the partial derivative with respect to W1 of our empirical risk. So that's the second piece of the puzzle. Taking a step back, we found two partial derivatives. This was the partial derivative with respect to W0. And this was the partial derivative with respect to W1. WRT here, as I'm saying, means with respect to. Okay, and so the plan now is to set both of these partial derivatives equal to 0 and find the combination of W0 and W1 that satisfy this system of equations, right? It's two equations and two unknowns. And so the specific way I'm going to go about doing this is to solve for W0 in the first equation, and that W0 is going to become W0 star because it's the best intercept. It's the one that has the smallest mean squared error. Once I have my W0 star, I'm going to plug it into the second equation to find my best slope, W1 star. Okay, and that'll be a way to solve the system of two equations and two unknowns. What questions do we have with what we've done so far? Okay, because things are about to get even messier. Let's do it. So we'll start by solving the first equation for W0. The result will be called W0 star. And our big picture goal here is to isolate W0. That's what we need to do. Okay, so using properties of sums, I want to write this as W0 equals some other sum. That's what we have to do. Okay? And so our first step will be the same as when we did this for mean squared error, which is to recognize that, well, this negative 2 over n doesn't impact our setup at all. We can multiply both sides by its inverse reciprocal, negative n over 2, and it doesn't change the equation, really. So I'll do that. And so I get this sum. And now remember, since my goal is to isolate for W0, it might make sense to break this down into several sums, like a sum of yi's, a sum of W0s, and a sum of these things. Because when I do that, I can try and separate for W0. One thing that might be helpful is to expand this parentheses. And when I do that, I can remove this parentheses, but there's one other thing I have to change. What do I need to change? Cushy. Yeah. I need to distribute the minus sign. And this becomes a minus as well. Okay? And now what I can do is, well, I got to get rid of this parentheses here. Break this into several separate sums. So I can write this as a sum of yi's minus a sum of W0s minus a sum of W1xi's. Okay? Now, to simplify this, I can use some of the properties I've seen in lecture and homework so far. For example, this is a sum of just constants, right? There are no i's involved here. And as we've seen before, this sum really just means this is equal to n times W0. Okay, so I can simplify that here. And then down here, W1, it's a constant. It does not involve an I. And so I can pull it out of the sum. right? This is W1 times the sum of xi's. That's 0. Okay? And now I'm pretty close to isolating for W naught. All I have to do is add this term to both sides and divide both sides by n. And when I do that, I'll have what I wanted before, which is W naught equals something. Okay? So I'm pretty close to that. Okay? What I'll do is add W naught to, n W naught to both sides. What that gives me is the sum of yi's minus W1 times the sum of xi's equals 0. Or not 0, sorry. N W naught. And so dividing both sides by n gives me W naught is the sum of yi's minus W1 times the sum of xi's all over n. But these terms seem familiar, right? When anytime you see sum divided by n, it should remind you of what? Good, the mean of that variable. Right? And so this is the mean of y's minus the slope times the mean of x's. So whatever my best intercept and slope are, they need to satisfy this. Okay? So this is a formula for the best intercept of a linear hypothesis function for making predictions. And it involves the definition of the best slope. Okay, so whatever the best slope ends up being, once I find it, I plug it into this, it'll tell me what the best intercept is. Okay? And just for concreteness, I can put in here that y bar, oops. Oops, y bar involves y. And x bar involves x. Now, does this look familiar at all? Yeah, it's the exact same formula we found in DSC-10. Okay, well, there we didn't find it. We kind of just told it to you that it was that. Or we gave a justification, but it wasn't as rigorous as this. But now we're seeing where it's coming from. Right? We solved it by hand. Okay? So we're almost there. Okay, only a few steps away. What I now need to do is take what I just found. So use W naught star equals y bar minus W1 star x bar, and plug it into this and use that to find what W1 star is on its own. Okay? So my goal here is isolate W1 star. Okay? So let's do it. Again, the negative 2 over n, we can multiply both sides by negative n over 2, get rid of it. So we're left with sum of yi minus, I'm going to, while I do this, distribute the minus sign here. So we get minus W naught minus W1 xi times xi, and that's 0. Okay? Now is the point at which I'm going to use the formula for W naught star that I found earlier. I'm going to come put that in here. Okay? And you'll see I'm going to rearrange things cleverly to make the formula turn out nicer. Okay? And that's one of the other principles that you're exploring in homework 1, which is that the solution shouldn't always be to multiply out every single bracket. Right? Sometimes you want to keep terms together because it ends up making the answer easier. Okay? And so, let's do that. Sum of yi's minus y bar minus W1 star x bar minus W1 xi equals 0. And remember here, my goal is to try and, well, let me toss a star on this xi too. My goal is to try and solve for w1 star. In doing that, I want to isolate terms that do have w1 star versus don't have w1 star. Okay, I should try and separate it. So what I'm going to do is separate this big sum into two smaller sums, one that involves w1 star and one that doesn't involve w1 star. Okay? And so if I expand out this minus sign, that'll help me get this to look something like this. And so I can write this as this, where this term and this come together here, minus w1 star times the sum of x bar minus xi, plus xi equals 0. Notice I can't drop the xi here. You got to be careful to keep that around. All I've done is broken this sum into two separate sums where in part of one, in one I could pull out w1 star, and in the other I couldn't. Okay, and why did I do this? Well, now I'm pretty close to having my answer. All I have to do is rearrange for w1 star, and I'm done. Okay, before I rearrange, I'm going to make one minor simplification here. Notice this first term is of the form value minus mean, and this is of the form mean minus value. Okay, and a common theme that you've seen in DSC 10 and here is we like to do value minus mean. So like for example, when we converted values to standard units in DSC 10, we did value minus mean divided by standard deviation. And so to keep things consistent with that, and to make our simplification easier, I'm going to switch this from mean minus value to value minus mean. But if I do that, there's something else I have to do. You have to switch this to a minus sign. And you see that now, when I do that, it makes it so that I can just add this term to both sides and drop the minus sign altogether. So when I do that, I'm going to switch the left and right hand sides here. My sum, xi minus x bar times xi, equals my sum of yi minus y bar times xi. And I'm done. Divide both sides by this thing. And it gives me, it's almost worse than the drilling, to be honest. Actually, I'm not sure. The drilling's pretty bad. But anyways, there's a formula for the best slope. So we find the best slope. Once we have that number, we plug it into the first formula. That gives us our best intercept. And we're done. We have a way of making predictions. Okay? So we know the best slope and best intercept for making predictions with a linear hypothesis function. Again, best here means smallest mean squared error. And why does it mean that? It's because we're using the squared loss function. Maybe you have a different way of thinking of what's best, and well, if you do, well then you have to minimize average loss for your loss function. But if we're using squared loss, this is the best line for making predictions we're going to have. Do you have a question? Was it related to that? Yeah, good. Okay, now these formulas work. Like we showed that they work fine, but the first formula, that is the one for W1, it's in a slightly less common and less convenient form. And so what I want to do is show you that it's equivalent to this other form that you'll see more commonly in the wild, and that you'll see is easier to prove is equal to the slope formula that we saw in DSC 10, because this is not the slope formula we saw in DSC 10. We'll talk more about that one, the one that involves the correlation coefficient, in Tuesday's class, but I'm going to rewrite the slope right now in a way that looks closer to what that was. Okay? And so my claim to you is that the slope is equal to this thing. And to prove it to you, what I'm going to do is show that the numerators are equal and that the denominators are equal. Okay? So I'm just rewriting this as this and this as this. Okay? And the key idea behind the proof is actually something we've seen many times before. It's that if you take up, or you take all of your values and from them subtract the mean and add all these deviations, you get what number? 0. That's always 0. Okay, we actually talked about it last class. And we also are asking you to prove it in homework 1. Now in homework 1, you can't say, we did it last class, or you can't also say, it's true because the deviation, the distances to the left equals distances to the right. No. What you have to do in homework 1 is expand this sum and then show using properties of the sum that it happens to be 0. Okay? But anyways, that's the key idea of the proof. And what I'm going to do is start with the right-hand side numerator, which is this thing, and show that it reduces to this. Okay? So I have the sum, xi minus x bar, y minus y bar. And what I'm going to do is distribute this first bracket. So I'm going to write this like two different sums, one of which is xi times yi minus y bar, and the other is x bar times yi minus y bar. All I did here was do first number times this minus second number times this, and I separated the two sums. Sound okay? All right. Now, x bar, that's a constant. I can take that out here. And I can write this now as the sum of, I'm going to change the order a little, y minus y bar times xi minus x bar times the sum of deviations for y. And what is this thing? 0, good. And so, this is just the left numerator. Okay? So I've shown this is equal to that. And we don't have all day, so I'm not going to do the denominator, but it's basically the exact same argument. You write this denominator as xi minus x bar times xi minus x bar, and follow the exact same argument, and the same thing will happen. Okay? And so this is the form that you might see most often, and we like it because it looks a little more familiar. Like I was saying before, the correlation coefficient version we saw in DSE 10, which we will revisit next class, it involves the correlation coefficient, which is the average of the product of x and y when both are in standard units. And to convert x to standard units, you do x minus mean of x divided by standard deviation. And there's a product of x in standard deviation, x in standard units and y in standard units. And it looks like there's also a product of x and y in standard units here. The thing is, we're just missing the divided by standard deviation. What does the denominator resemble? Yeah, it's close to the variance of x. It's n times the variance of x. clear. Okay. But in any case, we've now found the intercept and slope that minimize mean squared error.